Hello everybody, my name is Quinn Brownell, and today I will be talking about nuclear processes. So today the forecast will be you should know how to identify fusion, fission, and nuclear decay, and to go along with that you should know half-lives, and to help with this you will know the interactions between the processes and their forces. Now first we're going to start off with fusion. And fusion is defined as when two high-speed atoms run into each other to create one atom. Now this happens to combine two atoms into one and create energy. And this happens when the two atoms run into each other, obviously. And an example of this would be the sun. Now the sun has hydrogen and helium, and these two combine to create the sun's energy, which is transferred to the earth in rays. Now the sun is good and bad because you can get sunburn, which is the sun's energy, but it also heats the earth. Finally, fusion follows the law of conservation because nothing is created or destroyed in the process. Every new atom comes from the same amount of protons and neutrons in the previous atom. Now here will be a stop motion of how fusion works. So as you can see, we start off with two high-speed atoms. Now let's say that the top one, right here, is the helium inside the sun, and this bottom one will be the hydrogen. Now these atoms are going very high speeds, which cause the EMF to move closer because the protons inside the two nucleuses would usually repel these atoms, but since they are going very high speeds, this doesn't happen. Instead, it combines and creates energy. The two nuclei form together by the strong force. When combined, the leftover energy is released, and the energy produces light and heat. This causes one larger and stable nucleus to form, requiring less energy than before. Fusion stops when all the atoms have been combined. The next nuclear process we are talking about is fission. Now fission is defined by when a loose neutron runs into a large atom, making it split into two atoms. This is kind of the opposite of fusion. Now this happens to make atoms more stable than it was when one large atom was together. Now this happens when a neutron runs into a large atom. Now this is a loose neutron. And an example of this is uranium-235. Now when the nucleus of the larger atom splits, the uranium-235 separates into two different atoms. These atoms are now classified as rubidium and caesium. Now the law of conservation for fission applies because when the loose neutron hits the atom, it splits. No neutrons and protons are created or destroyed. Now for the stop motion. So let's say this is uranium-235. It's one large atom. And now we have introduced a neutron, a loose neutron that is flying towards this large atom. Now this loose neutron is going to hit the atom. The strong force will become disrupted, and it becomes weaker than the EMF force. But the strong force is still able to hold together parts of the nucleus, and that those parts are two different new nucleuses. So the strong force did become weaker, but the EMF is winning. Since the EMF is winning, the nucleus splits, and this creates energy. The atoms break and create energy. Also, they typically release 3 neutrons, as you can see here. And the new atoms separate. The next step would be nuclear decay. Nuclear decay is defined as the process of particles and/or energy leaving the nucleus. This basically means that the nucleus is radioactive. Now, the types of nuclear decay would be alpha decay, beta decay, and positron decay. You will also need to learn about half-life, but we will get into this a little bit later. The first type of decay is alpha decay. Now, alpha decay is defined as a process of decay when 2 protons and 2 neutrons are released from the atom. This happens to stabilize the nucleus of the atom. This happens when an atom is unstable and has too many protons and neutrons. Now, this follows the law of conservation because the atoms inside of the nucleus simply leave the nucleus, but are not created or destroyed. And finally, an example of this would be uranium-238, because there are too many protons and too many neutrons inside of the nucleus, making it not a representable atom, making it need to lose protons and neutrons. So let's say this is uranium-238, this atom right here. Now it has too many neutrons and too many protons. So it is going to release 2 neutrons and 2 protons. So basically it's going to release helium from the nucleus. Now, this is the law of conservation, because these neutrons and protons are released from this atom. They are not created or destroyed. It is now just helium. And this helium just goes away. And the nucleus is more stable than it was before. Next, we have beta decay. Beta decay is defined as the process of decay where a neutron turns into a proton. This happens to stabilize the nucleus of an atom, and it happens when an atom is unstable and needs more protons to stabilize it. Now, this follows the law of conservation because no neutrons or protons are created or destroyed. Now let's say that this atom is carbon-14. A neutron will come forward, as you can see here, and it will turn into a proton. Did you see that? I'll replay it. So it starts out as a neutron, and it turns into a proton. Now this will make the atom more stable, such as in carbon-14. Finally, for decay, we have positron emission. Now this is defined as the process of decay when a proton turns into a neutron. It's basically the opposite of beta decay, and it has the same reasons. Why? It stabilizes the nucleus. And it happens when an atom is unstable and needs more neutrons to stabilize it. It follows the law of conservation because there are no neutrons or protons created or destroyed. The proton just turns into a neutron. Now an example of this would be carbon-11, because it needs more neutrons and less protons. Again, let's say that this atom right here is carbon-11. Now, a proton will come forward this time, right here, and it will turn into a neutron. Finally, we have half-life. Now the definition of half-life is the time it takes for half of the radioactive atoms within an element to become stable. This happens after an object begins to contain radioactive material. A good example of this would be carbon dating, because carbon dating is used when carbon begins to contain radioactive material, which would be the carbon, and you can use the half-life to determine the date of how long ago this item existed. And finally, it follows the law of conservation because no atoms are created or destroyed. They are simply decayed and now they are stable. So this is what a half-life graph looks like. Now, theoretically, it's supposed to lose half of its radioactive atoms in a certain amount of time every single time. This is the idea of it. This is what is supposed to happen. Not all the time will you see this being perfect, but it will be very, very close. Now, as you can see, the number of radioactive atoms is on the side here, and the time in days is over here. So we start off with 80 number of radioactive atoms, and this is obviously at 0 days. Now, half of 80 would be 40, and this happens in 6 days. And then you keep going from there. So the half-life would be 6, and to check this, you can divide 40 by 2, which is 20, bring it over to the graph, and as you can see, it's another 6 days. Now, just to check it one more time, half of 20 is 10. Bring it over to the graph, and would you look at that, another 6 days. So this proves that the half-life of this graph is 6 days. Now review. So you should have learned fusion, fission, the nuclear decays, and finally half-life. Now, fusion is the combination of two atoms at high speeds. Fission is the separation of a large atom by a neutron hitting into the large atom. Nuclear decay, remember there's 3 types: alpha decay, beta decay, positron emission. And alpha decay is when helium, 2 protons and 2 neutrons, are released. Beta decay, a neutron turns into a proton, and positron emission, a proton turns into a neutron. The way that you can remember positron emission is it starts with a P and ends in an N. And finally, half-life is the time it takes for half of the radioactive atoms to become stable. Thank you for watching this, and I hope you learned something and enjoyed it. Thank you.